statistics that we want. Sweet. I like all of those things. That would be helpful. Compute. So let's see. The mean was 62 1/3. Or 2/3. Okay. So let's go back. 62 and 0.6. Actually, it's 0.7, really. Because we round to one more than the data gives us. The standard deviation of the sample is 19.8137. 19.8. Now, notice how it says standard error. We'll confirm this, but I'm pretty sure it did this. It did 19.48. Oh, 48. 19.5 divided by the square root of 15. Because that's what we need to do to be able to find the standard deviation of our sample. A lot of people call it standard error. Median, we don't need. The range, he'll look all the cool stuff. Okay, but before we do that, requirements. Well, we're finding a mean. We need the sample to come from a normal distribution to be able to use this formula, S over the square root of n. So how does that work? Well, the sample could be really, really big, and that would work. Well, 15 is less than 30. Oops. So we just need the population to be normal. Do we know anything about the population? No. Why would we know anything about statistics students and their ability to guess when a minute happens? So we just have to explore the data. A great way to do that is by making a graph, a box plot. So we have to click that, and it likes making horizontal box plots, or it likes making vertical ones, which is not what we usually do. Let's see. Look at all the options we can do. All right. Does that look bad? Does that look good? Does it look like there's any really... If there's an outlier, we'd have an issue. Essentially, what we're going to do is, here's our IQR. Our IQR is the width of that box. If we go the IQR outside this much, I think that's fine. Oh, there's the data. That's cool. Whoa. I had no idea you can do that. Whoa, clear. That was cool. So it looks like we got a pretty normal sample, which we can conclude that this came from a normal distribution. So pop is normal. Square root of s over, so the s over the square root of n is 19.5 over the square root of 15. So notice how that's the same same formula we used last time. 19.5 divided by the square root of 15. Yeah, 5.03. So when that thing said standard error, that's what it was talking about. All right. So to go further, we need to go to standard. We need to go to a point that splits the 0.05 in half. The alpha was 0.05. I can't put it all here or all here because this is a two-tailed test. We're going to split that in half. Alpha over 2. There's that symbol we all love. So we're going to put 60 in the middle, and I'm going to go out to a spot that splits into 5%. Here's the problem. We can't use 1.96. We can't use z because I don't know. We don't know the sigma. Okay, so we need t. So we can, if you have a TI calculator, you go to inft, or see a box plot, or we can go to calculators. T. This is a betweener. The degrees of freedom is 14 because, you know, sample is 15. I want to put 0.95 in the middle. 2.14. So what we just did was find out where in the T curve is that for the degrees of freedom is 14. 2.14. I think all we need is 2.1. T is 2.1. So just a little bit more than 1.96, right? The T is wider. So to find out where that number is, we're going to do 60. Notice the plus or minus. Oh, it's all coming back to me now. 2.1 times the standard error of 5.03. So 60 plus 2.1 times 5.03. And 60 minus 2.1 times 5.03. 70.6. 49.4. So does our sample fall in that? Yeah, our sample was 62. Green. So, wait, our sample is in our confidence interval. Let me draw the rejection zone. The rejection zone was split in half because it's two-tailed. So, oh my goodness. I am going to basically copy and paste the last conclusion. Did I just pick all fail to reject examples? Teachers should really do the math ahead of time. Okay. So we failed to reject. Well, really, since, check this out. Here's some math notation for you. Since 49 is less than what we got, which is less than 70.6, we failed to reject the null. There is not sufficient evidence to support the claim that the mean, the population mean, is not 60. There's a double negative there, but if we said there is sufficient evidence to support that the population mean is 60, that would be wrong. There's just not sufficient evidence to support the claim that it's not. So you can also say that there's not sufficient evidence to reject the claim that the population mean is not 60. The double negatives are really getting me. 8 minutes, I have a meeting with another class, which I'll probably just go on the deck and call them from. All right, now we're going to get into, let's see, significant levels. So the Brazil vending machine dispenses coffee. That's exciting. And a random sample of 27, I like that. That probably is N. Does that sound like N to you? This video's long. Ugh. You can't see green. And filled the cups, contents with a mean of X bar and a standard deviation of S. Use the 5.05, so there's our alpha, to test the claim that the machine dispenses amounts with a standard deviation greater than the standard deviation of 0.15 specified in the machine. So the machine is saying, look, our machine's great. We're going to tell you that the standard deviation of all cups is 0.15. That's our claim. Okay? But when the standard deviation is bigger, that means that there's more variation in the coffee that comes out. By only 0.17 ounces, which I can't imagine is a lot. But, you know, you want a coffee machine that dispenses the same amount of coffee. We want that standard deviation to be small. So let's use this sample to test the claim that it actually is more than what they say it is. So we are doing a standard deviation test. Everything's the same, except we're not using normal. We're going to use chi. How are we doing about pronouncing this chi square? Which is a... Right, standard deviations are skewed. So we need S. We need N. We'll need chi, but we'll do that later. What else do we need from that nice formula? I think that's it. Okay. We're going to find the chi value that puts 0.05 on the right. So let me draw my rejection zone. I'd say that the rule of having to draw a picture is even more important right now. The mean doesn't matter. All we care about is this value here, which is on the right. Don't worry about a confidence level. We're not doing confidence intervals in this one because... Wait, what's my null? And my alternative, my null is always equal, that the sigma is equal to 0.15. That's what the company thinks, but we want to test that it's greater than that. So we are doing a right-tailed. And let's see if we can finally reject one, huh? 0.17 is not far, so I don't know. Right-tailed test. So our S is 0.17. It gave us the mean to be mean. Get it? So the textbook was like, bleh. Here's a number you don't need. N is 27. So really, I think all we'll need is n-1, the degrees of freedom. Because that's what the chi depends on. 27, 27, 27, so it's 26. I don't know why that took me so long. Stat, calculator, summary, calculators, chi. There we are. Standard. Degrees of freedom is 26. Equals 0.05. That needs to be a greater than symbol. 38.885139. That seems really far from 0.17, but this is just on this curve. And we need to convert that. Chi square is equal to n-1 times s squared over sigma squared. So sigma squared is equal to n-1 over s times s squared over chi squared. And we're not doing variance, we're doing standard deviation. So we got to square root that. So what if we do 26 times 0.17 squared over 38 point 8, 9. So 26 times 0.17 squared divided by 38. So relative to this curve, we got 0.019. I have to review my notes here. Oh. Oh. Duh. We know what this is. We know what sigma is. Because we made a hypothesis that this is 0.15. Okay. Scratch that. Starting over. So we got s equal to 0.17. We're assuming that the sigma, based on our null, is 0.15. Based on these two numbers, we're going to find the chi squared that relates to that by doing n-1 of s squared over sigma squared. So 26 times 0.17 squared over what we're assuming. 26 times 0.17 squared divided by 0.15 squared. 33.39, and that is less than 38. We failed to reject again. Okay, so hopefully this video helped. The fact that I couldn't come up with an example for you that we actually rejected is a problem, but also it just means that if this was on the other side of 38, we would have rejected, and then we would have rejected the claim and been excited that it's greater than, but 0.17 was really close to 0.15, so we're fine. We can't reject the idea. We just had a bad sample, or they're just not happy. with their vending machine. Okay, peace.